My name is Amir Salaree, and I'm a PhD candidate from the Department of Earth and Planetary Sciences here at Northwestern. My research focuses on studying tsunamis and how they form and behave in the oceans. Today, I'm going to talk to you about perhaps the most precious and most important commodity in dealing with tsunamis. This commodity is time. On Christmas 2004, a magnitude 9.3 earthquake shook the Indonesian coastlines and created a monstrous tsunami that plowed throughout the Indian Ocean. This tsunami resulted in more than 250,000 casualties. The tragedy was repeated in 2011 when a huge earthquake went off near the coast of Japan and created a tsunami so big that it resulted in more than $300 billion of economic loss. But what could have been done? What could have been done to avoid the tragedy? What could have been done so that these people in these frightening pictures could have lived? What could have been done so that these people could have sent us these images instead of us finding photos in half-dead cameras over devastated coastlines? This is where my research comes in. Well, what do we know about tsunamis? Tsunamis are perhaps most famously associated with large underwater earthquakes. These earthquakes tend to occur at or around certain types of boundaries between huge chunks of rocks known as tectonic plates on the surface of the Earth. This map, for example, shows the location of these boundaries around the Pacific Ocean. The stars here show the location of huge earthquakes that have created devastating tsunamis throughout the Pacific over the past century. But how does an earthquake create a tsunami? Well, as a result of the motion from an earthquake, the ocean floor, here shown in brown, gets deformed. This deformation in turn creates a bump of water on the surface of the ocean. This bump of water is unstable and obviously cannot sit there forever, so it has to move around. It does so in the form of waves. These waves are known as tsunamis. Tsunamis can cross ocean at roughly the speed of a jet plane, so they move pretty fast. The shape, speed, and size of tsunami waves are, for the most part, determined by the depth of ocean at any given point. Therefore, in order to study the behavior of tsunamis, we would need reliable information regarding ocean depth. In other words, we would need a good topography map of the ocean. This data is known as the bathymetry. I use computer programs that use the bathymetry data as well as information regarding the earthquakes, let's say the yellow stars here in this map, in order to produce predictions of the tsunami behaviors in the oceans. The results of my work, or the results of these computer programs are known as Tsunami Simulations. The results of Tsunami Simulations are sometimes maps like this. This is a simulation of maximum tsunami wave height from the 2011 Japan earthquake. Japan is this long chain of islands here that you can see in this picture, and the earthquake is the yellow star. The map is color-coded according to tsunami wave height. So the dark red areas show the tallest waves, while the dark blue areas show those areas with really small tsunami waves, or perhaps no tsunami at all. In order to produce more realistic tsunami simulations, we would need more detailed bathymetry maps. More detailed bathymetry maps means a larger number of data points, and more data points mean that the computers would need to do more computations that take much longer to actually produce a simulation. But here's a problem. Remember, tsunamis cross oceans at roughly the speed of a jet plane. So after the earthquake, you don't have those many hours that you need in order for your simulation to work. Remember, your simulations are supposed to identify the most vulnerable coastlines, the coastlines most exposed to tsunami waves. You need to relay this information to the authorities in charge, and they in turn would need to issue evacuation orders and get people out of harm's way. So things work slowly. You would be tempted to speed your simulations up. One way would be to, just remove some of the data points from your simulations. Just remove some of the data points from computations, and your simulations would be faster. But the question is, how much resolution do I need? How much data can I keep in my, should I keep in my programs? How much data, in other words, can I take out without my simulation results to be changed at all, or very little? This is a complex question, or at least seems like a complex question, but trust me, it isn't. It is something that we actually deal with every day. We actually deal with this question every minute, every second of the day. To prove this to you, I'm going to ask you a question. Do you know this face? Just a quick show of hand here in the audience. How many of you recognize this face? Okay, that's reassuring. Okay, so otherwise I would have been in trouble. So this is my face. So would you still believe this is my face if I kept removing details from it? Perhaps I can't really submit the one on the right as my driving license photo. It probably doesn't really look like me, but you would agree that there can be found a middle ground. You can find a point at which you could say, well, you've removed some of the detail from your face photo, but it still kind of looks like you. This is the incredible talent that our brains have. Our brains can look for patterns, for borders, for features and things, and identify the differences and similarities between faces and objects. I can pose the same question to a tsunami. How does a tsunami see this bathymetry map? In other words, how much detail can I take out of this map for a tsunami to be able to still identify this map? How much detail can I take out until a tsunami says, hold on, wait a minute, this is a different map now, I have to behave differently because it's different. In order to test this, I can prepare several versions of the same bathymetry. Here on the top left, you see the real deal. This is the detailed bathymetry map of the Pacific Ocean, the one that we saw before. And as you move to the right, I have removed some of the details from it. So the one in the middle has some details, while the one on the right almost has no details. At each step, I can use my very same computer programs in order to simulate a hypothetical tsunami. Let's say a tsunami in the Northern Pacific. And this is what I get. These three maps are obviously different. But you couldn't deny there are striking similarities between them. This is very interesting. It seems that the tsunami is kind of like thinking my brain. It's looking for the differences, for subtle differences, for features in the bathymetry, and sort of adapts itself to the final product. So it works. You can actually produce a tsunami simulation, sort of valid tsunami simulations with less data. So while I would love to work with a sharp, crisp image of a tsunami, and while I can also take all the details out until I end up with a pile of bricks that no one can use and no one wants, in a pinch, when I don't have the luxury of time, I can work with a middle ground. I can work with a less detailed version of a bathymetry in order to produce a valid tsunami simulation just in time to save lives. Thank you very much.